Good afternoon. Welcome back to ECE 207. We're continuing in Chapter 14, but we really won't be there that long in Chapter 14. There is a homework assignment that has been made available, and you will want to check that. The problems that are being asked for you to work are different. These are now exercises, and the answers are there, or even some hints are there. So I realize that we're going through this very quickly, but I'm wanting you to be able to use the skills that you've already learned, which are KVL and KCL, to this new environment, which is an operational amplifier. You won't have to worry so much about what's going on internal to this three-terminal device. Obviously, we're connecting it to power supply, so don't forget that. But we're treating it as this box that does something for us. And what we want to learn is how to analyze this from a output or from an input-output perspective and not worry about what all the transistors are doing that actually create this operational amplifier. We want to use it as a operating box. No, exam 2 I have not even looked at. So I apologize, but there are some things that I'm having to deal with this weekend also concerning accreditation. And so your accreditation, you want to graduate from an accredited program. That's what we're pushing for. That visit will be on Sunday, Monday, and Tuesday of next week. That's consuming me at the present time. Question?
Can you then post the solutions at least?
I can try to post solutions to exam number 2. Would that make you feel a little bit better? I thought you probably already had those memorized and already worked out. That's what I used to do when I was in your position. I would go home, and at night I would be sleeping, and I go, or trying to sleep, and go, oh shoot, that circuit looked like what? Oh, now I remember. Never mind. Go ahead. Question? Oh, thank you. That would. I don't know if everyone heard that, but someone is volunteering to grade your papers. So maybe I will take them. Oh, we could do an in-class grade our own, huh? We also are concerned with ethics in this accreditation visit, and as a part of your training, you learn how to be a professional ethical engineer, and we would then test you to the extreme under that scenario, wouldn't we? Well, maybe we won't go there, but I appreciate your patience on exam number 2. Exam number 3 is on us in no time. It's 2 weeks from today. We are trying not to deviate from that. That will be Chapter 14 and Chapter 10 material will be on the exam. Your next homework assignment, homework 6, is due Tuesday. You will be, it's doing the exercises, a lot of it. 4 or so of those problems are exercise problems, not problems at the end of the book. Hopefully you can find those and follow through. The next assignment is obviously 7 days later, a week later. And then the exam is the following Thursday. And hopefully I will have a few days to catch my breath between the 9th and when our third exam is, so that we can be ready for that. And I'll try to have material for you on the web also in terms of worked problems like normal. And I'll try to post an old exam number 3. Hopefully it's somewhat consistent with that material. What I want to do today is work through some of this. If you can follow what's going on in the lectures, that should go a long way to helping you solve the problems in the homework. That's the idea. And again, what we are doing is we're applying our skills that we've learned, KVL and KCL and Ohm's law. We just have to remember that we can maybe relate different variables in different ways at different times, but those particular laws are going to be used frequently. We'll look at a couple of different inverting op-amp configurations. This is just how to connect different external elements around these op-amps or operational amplifiers. We'll look at a non-inverting op-amp, and hopefully that makes sense to you as far as what we're doing. In the inverting op-amp, we're obviously negating the input signal. That may or may not make any difference. If you invert an audio signal, you obviously wouldn't hear that necessarily. It would just all be in the same time sequence. It would just be flipped, and in time that means nothing basically to you. You couldn't hear that inversion because, especially if it's being played, that means nothing to you necessarily. But there are conditions where you want to preserve the sign of the signal that you're putting in, and that might require you use a non-inverting configuration. And then we will discuss an integrator circuit. We won't get there if I keep talking. So let me start, and I'm not liking what I'm seeing so far with the tablet. Now that I'm in a hurry, it's not wanting to behave. I could have guessed that that would happen. So bear with me. Not that I know how to fix this, but that's how to fix it. You know what? I'm going to leave it. You know what that says, don't you? You have shirts that have that on it. OP. Don't you? Ocean Pacific? I don't know. In this case, in this case, what I'm trying to draw, so you can already start to anticipate what I'm doing. You can start drawing an inverting operational amplifier, and it will be with a triangle. Let me do something. I was just in a meeting before this. I wonder what that is. Let's get rid of that. That was a 300-page document. Maybe that's why it was not liking what was going on. And if that's not cooperating, we'll go the other route. And so this will really allow me to be in a good mood if I now have to spend another hour recording the lecture after the fact. But I will keep the audio going, and hopefully I have some extra paper, and we will go with the Elmo. I'm sorry, you want it on both? I was going to, but I kind of wanted to see out of the corner of my eye if my computer was cooperating, but it really doesn't matter if it does or doesn't at this point. What I want to start with then is this inverting amplifier. And it's now looking like what we'd had before. Here's our inverting terminal. Here's our positive non-inverting terminal. That one will be grounded. Then we will have a input resistor, R sub I, and our input voltage. And that's the same ground, if you're concerned about what that is. We then have our output, V sub O, and we could possibly have a load resistor, R sub L, connected to that. And one of the key pieces that we want is actually this feedback resistor in order to keep things working smoothly or effectively. There's our And what I have not drawn on this is actually the power supplies. Here would be, let's say, the positive, and here's the negative power supply. But don't forget, these are active devices. We have to energize these operational amplifiers in order for them to work. If you don't turn them on, they're not going to do anything for you. They'll just sit there like a rock. They won't do anything. So you have to turn them in or plug them on. Plug them in. Here's, let's say, I sub 2. Here's a current I sub 1. And we could also talk about different signals. I'm not sure how much. Let's go through this a little bit more carefully right now. There's our differential voltage, V sub D. Here's my input voltage, I sub X. Here's my, I'm sorry, what did I say? That should have been an input current, which is going to be 0. These guys look like they're infinite impedance objects, and those currents flowing there ideally are 0. But let's just label those so that we know what is where. And we could also say, well, let's just talk about that particular voltage between the inverting terminal and ground. Question?
What is the VCC?
VCC is my positive power supply voltage. And minus VCC is the negative. And it doesn't have to be negative VCC. Negative VCC could actually be 0 volts, and VCC could be 12 volts. VCC just needs to be more positive than minus VCC. I just was wanting to be symmetric and labeled those as VCC and minus VCC. That's how we've plugged in our device. Those are the power supplies that energize that active device, which is our operational amplifier. Let's now try to solve this particular circuit. Any other questions? Question? Pardon? So, yes, we're going to, in this class, we will always have our currents going into the operational amplifiers. We are going to neglect those. They're effectively going to be 0 for us. So I sub X, all the current, so what that means is I1 is going to get to that node, and none of it's going to go to the right as I sub X. It's all going to go to I sub 2. That's basically what that's telling us. V sub X is this, if I put my ohm meter, my voltmeter, I would be connecting to that node, the inverting node, and I would be connecting this one to ground. That's V sub X, how I've labeled V sub X. Let's now solve that, or what does that mean in terms of a solution? What we're looking for is we are trying to establish a relationship between the output voltage V sub 0 and the input voltage V sub n, V sub in. In order to analyze this, or in order for it to be working in the linear operating range, we need to make sure that we have negative feedback. I won't typically do this necessarily, but I want to just talk about it one more time so that we're comfortable with what that means. And that's actually why I put the V sub X in there. In general, you wouldn't worry about that V sub X even being defined, but it makes it a little easier to talk about. Let's assume for this first piece of the solution, which is making sure we have negative feedback, let's go ahead and assume that V sub X is positive. if V sub x is positive, what happens to V naught? Or actually, even independent of what V sub x is, what's the relationship between V sub 0 or V naught and the differential voltage V sub d? If this was not connected to anything, if I just looked at and said, oh, what's V naught? That's going to be the open loop gain, the A sub OL, the open loop gain of my operational amplifier times V sub d. That's the relationship between V naught and V sub d. Now that we have this in an interconnected network, it's not going to be strictly that large. This R sub f will actually knock that down, but what we're doing here is just getting our thought process and seeing in which direction V naught is moving relative to V sub x. In this case, we know V naught is A sub OL V sub d, but what do we know about V sub d and V sub x? How are they related? They're just the negative of each other, aren't they? The negative terminal of V sub x corresponds to the positive terminal of V sub d, and the positive terminal of V sub x corresponds to the negative terminal of V sub d. Meaning V sub d and V sub x are the negative of each other. This says that we now have A sub OL V sub x. Meaning this is now going to be minus a large value if we didn't have that feedback in place, but at least this gives us the sign relationship between what's being applied to the inverting terminal of the operational amplifier and what's happening at the output. What we're doing, though, is this is not quite what we have, because we're measuring this signal and feeding it back through this feedback resistor. That's why the F subscript is in place. This is R sub F. That's being fed back to the inverting input terminal or node. Or in other words, we're feeding back a signal that is moving opposite to V sub x. So we have something that's V sub x right there at that inverting node, and we're feeding something back that's going in the opposite direction. That's going to try to drive this V sub d to 0. It's going to try to force that negative or the inverting node towards the positive node or to ground. And because of that, we can now use the constraint that we want, which is to basically have negative output feedback. And by doing that, we can now use this summing point constraint. Which allows us then to say that in our analysis, when we're analyzing this circuit's behavior, we are going to assume that there's no voltage between the inverting and non-inverting terminal of that operational amplifier. We are also going to assume that these currents going into the two input terminals of that operational amplifier are 0. That's what we're going to assume. And if the analysis ends up giving us a different answer, then we can basically go back and say, oh, that particular assumption must have been violated. But right now, let's we know we're living under that summing point constraint. Let's now apply KVL at the input. And if we apply KVL at the input, what I'm wanting to do is sum up voltages around that particular green mesh on the input side of that circuit. Or I'm starting at the negative terminal of V sub n, which says that I now have minus V sub n. I have a voltage drop determined by Ohm's law across that resistor. That's R sub I sub 1. And then I go through this negative drop, or I go into the negative terminal of V sub D. That's now minus V sub D, and that brings me back to where I started, or the sum of those voltages around that loop is 0. My summing point constraint, though, tells me that I can assume that that particular voltage, V sub D, is 0. That now allows me to say that V sub n, if I put that on one side of the equality sign and move the Ri on the other, I have V sub n is equal to R sub I sub 1. Or if I need it, I could solve that for I sub 1, and that's now Vn over R sub I. I can't erase that bottom line, but that's an R sub I. That's KVL. You're going to be playing with these all the time. The other relationship that I want to work on now is KCL at the inverting node. I tried to encircle with a dashed circle that particular node. Let's now apply KCL at the inverting node. And if I do that, I'm now concerned with the sum of the currents in or out, or the algebraic sum of the currents at that node has to sum to 0. Or I could say I1 seems to be coming into that node, and I sub x as well as I sub 2 are leaving. And our summing point constraint, or actually for all of this particular class, we can assume the current going into the input terminals is 0. We will set I sub x equal to 0, and now that establishes a relationship between the current flowing into the input resistor and the current flowing through the feedback resistor. And they are both going in the directions that have been indicated. I1 is going from left to right based on V sub n, and I sub 2 is also traveling from left to right. That's now the positive current. What am I trying to do? I'm trying to come up with enough equations that will allow me to find a relationship between this output voltage, VO, and the input voltage, Vn. If I now do one more equation, which really I'm going to, I guess to be consistent with my color scheme, I want to now write a KVL around the output path. Or I now have a KVL at the output loop. And if I do that, I now have plus V sub D plus R sub f I sub 2 plus V sub 0 is equal to 0. V sub d, again, the summing point constraint says that that's equal to 0. So that's what we'll do, is we'll set that equal to 0 and solve for V naught, or our output voltage. And our output voltage now becomes equal to minus R sub f I sub 2. But we know I sub 2 is equal to I sub 1. So let's replace that. This is now minus R sub f I sub 1. But what else do we know? We also know, we also know what I sub 1 is in terms of Vn and R sub I, right here. We just derived that from our input loop KVL. We can substitute that or replace that I sub 1 equation, replace it with Vn over R sub I. How did I get what? Which one are you wanting? This particular sign? Why is that plus? So now, why is that plus? If I go up to my circuit, the reason that that drop is plus is I'm assuming a drop from left to right across that resistor. And I'm coming up from here, so that's plus V sub D. You didn't have trouble with that. But now you're wanting to know, why did I say that's plus R sub F? Well, this current I2 is going from left to right, and that's the direction I'm moving in my KVL equation, so that's going to be a plus R sub F I sub 2. And then I come down, and the next thing that I experience a voltage drop is this output voltage plus V0. That's really just the passive sign convention with Ohm's law. I'm going in the direction that I really wrote my I sub 2 equation in terms of, and that gives me then a drop from left to right, R sub F I sub 2. Does that answer your question? If that's true, now we actually have a relationship between the input voltage Vn and the output voltage V sub 0. We can pull out the different R's or combine those together, and we have minus R sub F over R sub I times Vn. That is now our input, that is now our relationship for the way that we interconnected this operational amplifier. What did we do? We plugged it in. We applied a plus VC and a minus VC. That energizes it. Now we connected two resistors around it, and we're applying an input voltage Vn, and we're connecting it to a load represented by R sub L. And Vn now behaves according to this relationship. The sign gets changed, and it gets scaled by whatever the ratio of R sub F to R sub I, or R sub I equals. Here are some observations that we can make.
I don't understand why we can assume IX and IY are both 0.
That's the property of this operational amplifier. It's basically, remember our original ideal operational amplifier concept, and that was that the inputs, where are they going? It looks like they're going off to nothing. And when we opened something up, what current is flowing out that top node on the right? There is no current flowing, correct? There's nowhere for it to go. It's It's like you're going up to the Grand Canyon and there's nothing to walk across. You're not going to go across, right? So that's what is happening. This is the ideal behavior of the operational amplifier. It's like there is nothing, nowhere for that current to go, and it's not going to go there. It looks like an infinite impedance beyond that top node. So at that top node where we wrote our KCL, I sub 1 is going there. It looks directly in front of it, and it says that looks too resistive. It's too much there. I'm going to go up, and all of me is going to go up. So I sub x by the design, that's what's underneath this triangle. All of those transistors and resistors that were used to create this device forces those relationships to hold. And that is, it makes it look like there's an infinite impedance to I sub x. If that's the case, then it's going to be 0. There's no current flowing.
Why not simply have no wire there?
Well, if there's no wire there, what we want is we want a voltage to be applied to that particular pin. We could care less if there's current going. Well, actually, we don't want any current flowing, but we do want to worry about the voltage or the potential at that particular node. So we do need it to be connected. And it is connected to these other locations in the circuit via these resistors R sub I and R sub F. So the fact that there's no current there doesn't mean nothing's happening. There's something happening, and what is happening we just derived, and that's this relationship. We just derived this relationship holds for those particular conditions that are happening with that operational amplifier, and that's what I wanted to try to point out via these observations. What's actually going on? We have negative gain amplification. Was there another question? Well, the reason why, well, they need to have external power sources because there's all these transistors that are inside that device, and they need to be energized in order to work. They need to be set at a particular condition. And a colleague of mine basically says, if you want toast in the morning, what do you do to your toaster? You plug it in. If you wanted this op amp to work, you have to plug it in. And that's what you're doing with V sub CC and minus V sub CC. You're plugging it in. It's not going to work otherwise. Now that you have it energized, it has these particular features. That is, those currents I sub x and I sub y are 0. V sub d, if it's in a linear operating range, will be 0. And that results in negative gain amplification. That's all that particular expression says, or that's what that expression says. So what's happening is we're getting something, it did not say that there's no current coming out of the op amp. We haven't said that at all, and there is actually current going out. What it's saying is the current coming out of that op amp is enough, and so we have to worry about this, but right now let's not worry about it. It's enough to whatever load we hang on there, it's going to preserve, it's going to give a V naught at that load. So now that will produce a particular current through it, flowing through R sub L. You're going, well, if no current's coming in, where's it coming from? Well, it's coming from these batteries. It's coming from where you plugged your toaster in. It's coming from VCC and minus VCC. You do have current coming out of that op amp. And that may be and that will be in addition to I sub 2. So your output current is not just I sub 2. You have this guy being energized by your supply. So I think what we'll keep going, and as you gain a little bit more comfort with these relationships, it will start to hopefully make some sense. But obviously we're starting to run relative to how you want to feel like we're going. So you're going to have to just accept some of these conditions on faith, and if we get a little bit further, we'll understand how to connect transistors to make them behave the way that we're talking. But we're assuming right now that that's going to happen. The output voltage, if you look at that equation, that output voltage does not depend on the load resistor. Do you see R sub L in the VO equation at all? Do you see R sub L? It's not there, is it? That V naught equation only depends on R sub F and R sub I. Because of that, this particular device looks like to that R sub L, the op amp is providing zero output impedance to that load. It's not impacting that load at all. It's just supplying the current that it needs, and it's not loading that resistor at all. Another observation that we can make is that our input impedance of this circuit equals this input resistor R sub I. And we can see that if we simply say, well, my input impedance must be the input voltage divided by the current flowing into that terminal. And that current was I sub 1. But if we go back to the relationships that are being in existence, which was just this one, now I have to learn how to do origami to lecture, folding paper. If you look at this, now you have Vn is equal to R sub I sub 1. If you solve that for the ratio Vn over I sub 1, what happens? You just get R sub I out, and that's all we're saying here. The input impedance, that's something, if you attached this inverting op amp or inverting amplifier to another circuit, it would look like you didn't attach it there at all. It would not load what it is that you attached it to. Well, it does in that now, I'm sorry, I was thinking that R sub I was infinite. Now it has a finite amount. It will load it in the amount of R sub I. The other thing that we can observe is that the gain is determined by the ratio of these two resistors that we connected around that operational amplifier. We just have to go into the shop or to the store and pick off the shelf a resistor R sub F and a resistor R sub I. If we wanted a gain of 1.5, we just have to make R sub F 1.5 times bigger than R sub I, and we have that gain. If we wanted a gain of 2, then R sub F needs to be twice R sub I. If we wanted a gain of 1/2, we would make R sub I twice as big as R sub F. So theoretically, these two resistors could be anything. But you know, anytime somebody says theoretically, there's always another phrase. Practically is another matter. Practically, R sub F and R sub I, we should make sure they have a couple of different conditions or relationships. They should be let me say I, they should be big enough or large enough to not draw too much current from the power supplies. And I would refer us to figure 16 in chapter 14 to look at that. Meaning if they're small, then you put a current over it, and now that current divided by the small resistor is how much current's flowing. And we really don't want a lot of current flowing. That's just sucking power, or taking power, or consuming power. So we would like R sub F and R sub I to not be too big. Not be too small. They want to be large enough so that they're not drawing a lot of current. But obviously, they can't be too big. And not so large to be unstable, meaning if you request them to be really large, it may be hard to make them that big, and meaning their value might not be very predictable or stable. So not so large to be unstable in value, or prone to injection of unwanted signals. Now let's just cut to the chase. You could care less about those two bullets, or I and I. What values can we use, right? That's what you're asking. Let's just pick some, not two, but let's define a range. Usually you would want these R's to be living bigger than 100 and less than a megohm. That would be a reasonable range for your resistors that you are now attaching around these operational amplifiers. And in this case, you're putting those in a configuration to produce an inverting op-amp. As an example, if we wanted a gain of 10, we might select 5% resistors having values of R sub F, let's say, equal to 5.6 k ohms, and R sub I equal to 560 ohms. And if you want to, you can go back. I'm sure you're all going to go back as soon as we dismiss today and read and study, memorize Appendix B. Appendix B you can look at for different values of resistors. Question?
When you say 5% resistors, that's the error.
So what am I meaning when I say 5% resistors? Do I have that? No, you actually have a problem on that. But that means that if you have a 5% resistor that was a 1 k ohm resistor, well, let's use something that's easy. Let's use 100. So now if you have a 100 ohm resistor and it's a 5% resistor, you're being guaranteed that that's within 5% of 100. So you pull it out of the bin and you're guaranteed that that's either going to be, it's going to be between 95 and 105 for its value. That's what we mean by a 5%. You may have a 20% resistor, and which do you think costs more? The 5%. So in the lab here, I don't remember. I think we probably have mostly 10% resistors. 1% resistors get a little pricey. 20% resistors are pretty inexpensive. And that just means that if you had 20% resistors, that 100 ohm could vary as much as be 80 ohms or 120 ohms. And you may or may not want that much variation in your circuit. It depends on what you're trying to do and your design. Other questions? Question? What causes one? Oh, you did have to ask that. Price. It costs more to make a more accurate resistor. It's just basically the tolerances and the accuracy or the time and effort that is put into. Some very accurate resistors might be wire wound. Some are just composites, and those can be put together quite quick or very rapidly, but there might be a fair amount of manufacturing tolerance issues involved, and so you might be able to create these 20% resistors pretty easily. But it is probably a good objective to not be having a broad range of resistor values. It's a good objective to limit the range on these resistor values. Let's look at another inverting amplifier. And this must be coming to us via figure 14.6. And you may want to give yourself a little bit more room than what I did up above your triangle. I now have a resistor there, another resistor here to ground, a resistor there, and all of that is in my feedback path. And here is now my output voltage V0, my load resistor R sub L, all connected to ground. The input waveform is V sub n. Here's our input resistor R sub 1. The next resistor, I'll get very creative. That's R sub 2. This one is R sub 3 and R sub 4. And let me, just because I'm going to refer to those, I'll call that I sub I, and that's V sub I. I also will be using a current I sub 1, a current I sub 2, and notice my directions. There may be or may not be a reason for labeling these directions in the orientation that they are. I sub 3 is now coming up from ground, and I sub 4 is going down towards the positive output terminal. That's now my interconnected circuit, and you get to analyze that. Or that's, I think, actually one of your homework problems. So if you follow along, you should be able to just reproduce that for one of your assignments. The analysis starts off in what way? Well, we really want to make sure that we have negative feedback, but typically when we are feeding information back to this inverting node, we have negative feedback, typically. So we should make sure that you could analyze that. You could say, okay, suppose that Vn is positive, then what's going to happen at V0? Well, that's going to actually give you a minus V sub D, which will get amplified, so you're feeding back a negative signal, and you put in a positive, so it is trying to force that positive signal to a smaller value. You are trying to squeeze the two input terminals of your op amp towards each other, or cause V sub D to equal to 0. And in this case, I guess I labeled that via V sub I, but that's the negative of V sub D. But if we make sure that we have, and we just did by what I just said, I did earlier. I'm trying to go quick. So here I stated it. What you would do is you would say, well, here's my V sub I. Let's say that V sub I is positive. Then what does that say? That says V0 is going to be, and this is V sub D, isn't it? Between those two terminals, and V sub D is plus to minus the way that it's drawn. V0 is this open loop amplification times V sub D, but V sub D is just the opposite or negative of V sub I, and so V0 is going in the opposite direction of V sub I. So we have negative feedback. That's now the parenthetical thought that we've done to convince ourselves that, okay, this guy should be operating with negative feedback, because we have something positive and we're driving it back against that positive behavior. If that's the case, then we have this SPC. Everybody can text that tonight. Summing point constraint. And you'll go, come on, Mom, didn't you know that? I'm talking about a summing point constraint. So the SPC ensures that this I sub I is 0, and, well, actually we want to ensure that V sub I is 0. We're going to have, by construction, that our input current to that node, both inverting and non-inverting, are equal to 0. If that's the case, what is happening here on this side? What I would like for you to be able to see is the right side of that R sub 1. Yeah, the SPC is the summing point constraint. I wasn't very clear on that, maybe. But now if you look at this, the right side of the resistor R sub 1, it's effectively tied to ground, isn't it? Because V sub D is 0. If that is tied to ground, that's exactly the same point as right here. Meaning I have this voltage dropped completely across R sub 1. That's just Ohm's law. That says then that I sub 1 is Vn over R sub 1. Whoops. Is everybody okay with that? I can also do what if I do KCL at the inverting terminal, or at the inverting pin of my op-amp? What does that tell me? The summing point constraint is active, or I have zero current in I sub I. If that's the case, then I hope it doesn't take too much convincing to convince you that I sub 1 is equal to I sub 2. Now we can do the following. Suppose that I do this KVL. What if I come up here and go here and then go right to there? That's the same, that point right there, that's like finishing up down here. Is that okay? Because it's the same ground. This point right here is the same as that point. Those red and green pins, the ends of those are physically connected effectively because they're both at ground. Question? That's true for all ground. Yeah, it's like a rabbit hole, I guess. You pop it in. In reality, that's not necessarily the case. You have to worry about ground loops. But in this class, in this analysis, that is the same point. It's like those 2 points are connected with a wire. Is that okay? So if we're doing our KVL, once I get to the red pin, I'm actually down to the green pin. I'm done. I'm back where I started. Is that okay? If I now write KVL for that particular, what do I want to call that loop? Let me call that M. I'm running out of creativity here. So if I now say KVL around M, I could now say that that's minus V sub I plus R sub 2 I sub 2. What's my next drop? Minus I3 R3. Is that correct? Why is that true? Because you're going opposite to the current the way you defined that current. Are we okay with that expression? That's just KVL, and it's consistent. We're just living with what we assigned. We assigned some currents, and we're now living under those assignments. Question?
V sub I would be equal to the negative of V sub D.
Yes, so V sub I is the negative of V sub D, and so what do you think V sub I is?
0.
It's 0, based on our summing point constraint. So I just included it so that you knew where we were going. But that's 0. That now allows us to relate R sub 2 and I sub 2 and I sub 3. We now know that those are just a constant away from each other. And if R sub 2 was the same resistor as R sub 3, I2 is the same as I3. If they differ, then that will just mean I sub 2 is fractionally related to I sub 3, whatever that fraction might be. Questions on that? What if I now, so what am I trying to do? I'm trying to solve this crazy circuit. By that, I mean I'm trying to get a relationship between Vn and V naught. I'm not there yet, am I? I'm basically halfway through the circuit in terms of working my way from left to right. I have a relationship on Vn and I1. I have a relationship on I1 and I2. I now have a relationship between I2 and I3. We could make a movie out of this. There's a lot of relationships going on. Any of you in the theater department? Then we want to get a relationship between I sub 3 and I sub 4 or I sub 2, right? We're engineers, we're not thinking that way, I guess. Let's look at KCL here at 2. What if we write KCL at 2? Aren't you glad you learned KCL and KVL? This is easy, isn't it? What's that KCL relationship? You have two currents coming into the node and one leaving. So that says I2 plus I3 is equal to I sub 4. So now we have a relationship there. We still don't have a V0 anywhere, so let's make one happen. Let's do the following. How about if I start here with a KVL and I go there, and then I come all the way down here, and I'm really back where I started because that's ground. So let me call that, wow, I'll call that loop 3. Is everybody okay with that? Again, that's the same ground. We're starting at ground. We go up through R3, across through R4, and then down through V0. And KVL now, I'll say that's KVL at the output. Well, I'm going to have to do some folding. And that wasn't my paper that was squeaking while I folded it. This is now KVL at 3, or at the output, and that says that I now have R sub 3, I sub 3. I'm going to have to do a little bit more time now on my nails, aren't I, if I have to do these lectures? Sorry. R sub 3, I sub 3. Now I'm going to be really self-conscious. Can I write the rest of the lecture without exposing my fingers? I could do it like this. Plus, now you're all going to be looking at my... Why did I say that? Plus R sub 4, I sub 4, plus V0 is equal to 0. Is that okay? That now allows us to solve for V0. V0 is minus R sub 3, I sub 3, minus R sub 4, I sub 4.
Does that mean we had to have chosen the wrong direction for I3?
Does that what?
Does that mean we chose the wrong direction for I3?
No, the question was, does that mean we chose the wrong direction for I3? No. It's just that we now have V0 is maybe an inverted voltage relative to I3 and I4. That's all, in the way that we picked it. And I hope that it becomes clear that maybe I3, the direction that we selected, might make this a little easier to analyze. But now I have, because now you're going, so what? This looks like it's worse than anything we could have imagined. We have a V0 with I3 and I4, but we know how I3 and I4 are related. They're related to I2, aren't they? Well, actually, I3 is related to I2, so we now can say I4 is a function of I2. But what do we know about I2? It's the same as I1. And what do we know about I1? Somewhere in this, we know I1 is related to Vn. Now we have, if you followed that, were you following your tail? We've caught our tail. We've started with Vn, went to I1, I1 went to I2, I2 went to I3, I3 went to I4, I4 and I3 go to VO. Follow that? Good. So we're done. Have a good weekend. No, let's finish it up. Oh, I know. You were okay with that finish, weren't you? When I was writing this up, I said, now what? Now what? I just told you. So let me write that out. If you didn't follow, now you can go home and read your notes and you can go, I don't have any idea. He got to talking with V1, I don't know. So we are looking for V0, which is our output voltage. We want to find an equation with that output voltage in terms of, or relative to, the input voltage. And now let me just write down what we had, or what I was saying rather quickly, but I was hoping that you kind of followed. We know that I1 is Vn over R1. That was our first relationship, and that was just Ohm's law at the input terminal. And we also know that I1 is equal to I2, and the reason that is because this op-amp is not accepting any current at the inverting node. So I1 is equal to I2. We know those are true. And we just found earlier, we found that R2 I2 was equal to R sub 3 I sub 3. That was why maybe we chose I3 in the direction that we did. There's no negative sign in this relationship. So I sub 2 is just a constant away from I sub 3. I can now solve this for I sub 3 and say that I sub 3 is R sub 2 over R sub 3 I sub 2. That now allows us to finally end up with our output voltage V0, which was this minus R sub 3 I sub 3 minus R sub 4 I sub 4. Let's replace that with what we know it could be. We know that I sub 3 is R2 over R3 I2, and R sub 4 because of KCL at whatever node we labeled it, node 2, we knew that I2 plus I3 was I4. And if we can put everything on the right in terms of I sub 2, that's the same as I1, and we know what I1 is in terms of Vn. That was our first equation. And let's now just do that. We now have V0 is equal to minus R sub 2 I sub 2. The two R sub 3's cancel. But I sub 2, so I'll just correct that. I sub 2 is I sub 1. So I did two steps, canceled and substituted I2 for I1. And we also have minus R sub 4. I sub 2 is just I1. I sub 3 is right here, R2 over R3 times I2, but I'm going to remember that I2 was I1. Or I now can put all of those together and I have R2 plus R4 plus R4 R2 over R3 times I1 is V0. And I know what I1 is in terms of Vn. This is now R2 plus R4 plus R4 R2 over R3 times Vn over R1. And we can now pull all of those together if we want. We have R2 over R1 plus R4 over R sub 1 plus R4 R2 over R1 R3 Vn is V amp. And that's now the, what do we know about our R's? Those R's are positive. So they're not going to change the sign inside that square bracket. And this is now what we started out saying we were going to analyze, and that was an inverting op-amp. Suppose that I said, well, this looks kind of ugly. Well, if you said, all of those are equal, and let's just pick a number, pick any number, a number between 500 and 1 meg, let's say 5,000. 5K, it doesn't really matter, but we want it to be between 500 and 1 meg. What happens? What's V naught? R2 over R1, 1. R4 over R1, 1. I'm running out of hands. R4, R2 over R1, R3 is 1, so 3. We just scale this by 3, and we're relating our input voltage, Vn, to the output voltage by an amplification of 3 and a sign change or an inversion. Questions on that? How about if we start another problem? Well, your homework is due on Tuesday. Let's look at a non-inverting. We have another 30 minutes, depending on whose watch we're using. If we look at a non-inverting amplifier, which is 1411 figure, what I'm wanting to show you here is that you do not always have to apply your input through the inverting pin on your amplifier. Now what we're going to do is we're going to feed this through some feedback resistors down to ground. We'll call this R2, this is R1, here is our ground, and now this non-inverting node is what we will apply our input voltage to. Here is our output V naught, and we can connect a load to that. What I want you to do tonight is to go home and analyze this circuit and convince yourself that V naught is actually 1 plus R2 over R1 Vn. They still think it's Halloween. They came to the door. Oh, I'm sorry. Now, what are we going to do when we analyze this? If we assume this is still negative output feedback, which it is, because we're feeding back the output to the inverting terminal, what do we know? We know that differential between the plus and minus terminals is 0. If that's 0, what is Vn? Vn is applied right across basically R sub 1, isn't it? And how can we relate Vn to V out? That's just a voltage divider. Or do a KVL around the output and find that relationship between the voltage dropped across R1 and the voltage at the output V out. And that should help you create or come up with this relationship for Vn and V out. We'll pick up at that point on Tuesday.